Okay, let's get started. So, the problem sets is due is today, right? So make sure you send that in. And I'll post the next one today. It's not quite ready yet, but probably later today sometime. Okay. Oh yes. Also, I'll give you a take-home quiz on Tuesday and give you a week to work on that also. But next Tuesday. I haven't prepared it yet. So, okay, that's it. So let's begin. We only have about 5 more classes, and we have to explore bipolar junction transistors, which is the next chapter. And I want you to get some feeling for how integrated devices are made. So we'll look at chapter 9 as well. So I have fixed the last few weeks of the schedule fairly tightly, I guess. So we'll try to be on schedule there. Okay, so let's begin right about where we left off. So we talked about Mosfet capacitors. So I'm going to skip that. And the problem set, this next problem set, you will get a chance to kind of play around with quite a bit of the Mosfet capacitance and so on. So make sure you understand it conceptually, because it's perhaps that's quite one of the most important parts, other than the current voltage characteristics of MOSFETs when you come to designing integrated circuits. So that's something you should try to understand well. So the MOS field effect transistor was what we saw last, and we will come back to this today. So let's review very quickly the idea. Okay, so the device is there. So you have a substrate, you have a source, you have a drain, and the source and the substrate are reverse biased. Okay, normal operation. Drain and the substrate are reverse biased under normal operation. Okay, if you don't reverse bias them, then you will lose control essentially. Okay, you can think about that. And you have a gate voltage which controls the channel between the source and the drain. So the input voltage comes across the source and the drain. The output current is the current between the source and the drain, and the control is at the gate. Okay, and typically the body or the substrate is connected to the source, to the drain. Sorry. Okay, the drain and the body are typically connected together. And we'll come back to that. That turns out to be an important point. Now, of course, the physical mechanism is that when you, in the case of the p-type substrate, you apply a positive voltage, which, yes?
I was just wondering, in the examples that we've been talking about, for the most part, have we been connecting the gains of the body?
Yes,
with
yeah.
What we've been
we have ignored the body so far because it's not so important. Okay. Yes, we assume that for everything we talked about so far, the drain and the substrate are basically connected, which means that this drain and this substrate has zero bias. Okay, this reverse bias junction is essentially shorted, which doesn't change anything except very minor things that we will talk about today, hopefully. But everything else is the same. So don't worry too much about it. It's important when you talk about billions of transistors on a chip. And we'll talk about that briefly today. That's the only situation where it becomes very important. But the physics is very straightforward. You apply, in this case, a positive voltage. You push the holes away. You attract the electrons, make an N channel. So you make an electron channel. And then the current can flow. Okay, the more positive you make it, the more electrons there are. So current will increase after some point when pinch off happens. And pinch off in this case is where the depletion region eats into the inversion region. Okay, which is basically what this happens. So the drain to body, of course, at some point becomes zero, which means that if they're connected together, this depletion region will basically meet the inversion region. Okay, the inversion disappears essentially. So you have pinch off and you have saturation. So saturation is where you operate the transistor to get amplification. If you just want to use it as a switch, you can operate it in the linear region if needed. Okay. Okay, so those were the few things we talked about, and I'm going to skip through this part. Now we derive the capacitances which we saw 2 classes ago. Oops, did we not? Oh, we did not, sorry. My mistake. Okay, we got to go through this. This is where we stopped, right? Yeah. Last class. Okay. Okay, so that's the picture. So let's keep, I got confused. So let's look at this schematic. Okay, we're going to, so the goal next, in the next, this part of the section is to understand the current voltage characteristics of the MOSFET. In other words, how does the drain to source current change with the drain to source voltage? So far, we've talked only about the gate oxide semiconductor interface. We looked at the capacitance of that. That's all we've done. Now we need to look at the actual characteristics of the MOSFET itself. That's the goal. Okay, that's the picture. Now look at the schematic here. This is what we will keep in mind. So the coordinates are x along the channel length, z is the, I guess, out of the plane of the screen, and y is perpendicular to the gate electrode. Okay. So we have a metal gate electrode, silicon dioxide insulator, and we have the immersion channel, you have depletion region, and you have the substrate and so on. And you have drain on this side, source on this side. Current flows, of course, from source to drain. Okay, electrons flow from drain to source. Okay, so far so good. So, and the gate, again, the voltages we are going to, so the goal again is to relate the drain to source current, okay, sorry, the source to drain current to the source to drain voltage and the gate to source voltage. Okay, so everything is, all the voltages are relative to the source. So you have gate to source voltage, which we will just call VG, and you have drain to source voltage, which we'll just call VD. Okay, and then there's source to drain current, which is just called ID. Okay, so those are the things that we're trying to relate. Okay, so first of all, we know that the gate voltage, which we saw in the last class, when the gate voltage is applied, some of the voltage is dropped across the oxide, and some of it is dropped across the semiconductor to do the band bending. Okay, so that's straightforward. So we derived this last class. So essentially, we have that part, which is the surface potential, which is the band bending to create the inversion, strong inversion situation. And then we have this part, which is essentially whatever drops across the oxide and whatever is required to compensate for the work function difference between the metal and the semiconductor, which is the so-called flat band condition. Okay, so we have flat band voltage minus Qs over Ci, where Qs is the surface charge at the interface between the semiconductor and the oxide. Ci is the capacitance per unit area of the oxide. Phi s is the bending. So these are the three terms that you need. That's how the gate voltage gets split. Okay, you apply gate voltage, this is what happens with it. Okay, so the picture is that. So let's look at each of these terms carefully. So, okay, so again, the goal here is to relate how the gate voltage controls the channel, because the channel controls the current. Okay, so keep that picture in mind. Okay, so the term Qs essentially are the total induced charges, which of course come from both the depletion region, which are fixed charges. Okay, in the case of p-type, they're acceptor negative ions, and mobile charges, which are holes and electrons. Right, so it's a combination of both. Okay. Then the mobile charges, so we can relate this, the mobile portion of that, to, so okay, this is one step jumped. So Qs is essentially Qn plus Qd, Qd being the fixed charges, Qn being the mobile charges. Qn is the inversion layer, basically, the electrons, okay? So you plug that in here and you reverse the equation, you get that. So what we have done here is we have related the charge in the inversion layer to the applied gate voltage. Okay, think about that for a second. We apply a gate voltage, we want to know how many charges are in the inversion layer because we want to calculate the current. That's what's happened there. Okay, the applied gate voltage has to contribute to many terms. Okay, in fact, 4 terms, right? The flat band term, the band bending, then the mobile charge, then it has to match the charges because the charges have to cause potential drop. So you have fixed charges from the depletion region, mobile charges from the inversion region. We're interested in the mobile charges. Okay, that's basically what that equation says. Okay, so now you've related how much charge is there in the inversion region to the applied gate voltage. Everything else is basically parameters from the device. Okay? Okay. The voltage, of course, required for strong inversion changes along the channel. Okay, that's another important factor. So if you look at the channel, the voltage drop is always referred to the source. Okay, so the voltage from the drain to the source is very high. It's whatever is applied on the drain. But as you go down the channel, that voltage drop decreases. Okay, as you get close to the source. At some point when you're at the source, the voltage difference is zero. Right? So the voltage has to drop just like we had for the JFETs, the previous field effect transistors, okay? Junction field effect transistors. So we can relate the band bending that is required to the local potential of the channel, okay? Which is very similar to what we did for the JFET if you go back and look at it. So essentially, you can relate, that's this term right here. 2 phi f minus Vx minus some term. Okay, ignore that for now. We'll talk about that in a second. But essentially, that's phi s. Okay? So when Vx is 0, which means when you're out here and the potential drop is 0, you need to have 2f for strong inversion, which is the same as what we had before. Remember, that's part of the threshold voltage. Okay? As you get closer to the drain, you need to get more voltage there. Which is why at some point near the drain you will get pinch off. Okay? Okay. So you have to think about that a little bit. But essentially what we are doing is we are substituting that with this term here, where Vx is the local potential of the channel. Also, with all the voltages that I'm talking about are always related to the source. Okay, now let's think about the last term here. The last term here is very straightforward. It's just how much depletion charge is there locally in the channel. Okay, of course, that depends on the width of the depletion region in the channel. And clearly from the picture, you can see the depletion region is wide here, and it gets thinner as you get close to the source. And that's, of course, because the reverse bias across that junction is getting smaller. Okay, here is more reverse biased, whereas here is less reverse biased, right? Because of the V-axis changing. Okay, it's getting 0. This is getting more reverse bias, right? Because positive voltage. Remember, it's N plus P junction. Okay, so that is just the depletion charge, which also we derived, I think 2 lectures ago. But essentially, it depends upon the local potential, which is shown here, and the doping concentration. Okay. So now if you look at this equation, we have a way to relate the local density of electrons in the channel, in the inversion channel, as a function of the applied gate voltage and the local channel voltage. Okay? That's all we need. Okay? So the gate voltage is the control. The channel voltage is actually the input, because you can relate that to the drain. Right? It's whatever is dropping from the drain to the source. So you can always relate that to the drain voltage. So those are the 2 unknowns we have, and we are trying to calculate the current. Okay, so that's the picture I want you to keep in mind. If you get lost in the actual derivations, it's okay, because you can go back home and derive it, but make sure you follow the logic. Yes?
I just wanted to make sure, I'm assuming that they're getting QD from equation 632 in the book, but there it uses Fiat instead of...
Yes. Why? It's a good question.
Instead of Fiat. I don't really know.
Because there's a local potential here. The bands bend differently across the channel. So if you look at the channel, the width of the depletion region depends upon how much reverse biased is the substrate with respect to either the drain or the source. Right? That's where the junctions are. And if the local potential across the inversion layer changes, you expect that depletion region to change. It's very similar to the JFET situation we had. Yes?
So basically for equation 632, they use VF specifically because
it's at the source.
Non-bending.
Yes.
Specific.
Exactly. It's at one location. Okay? So, but this exact equation is something we derived before, so you can go back and look at it. Okay. So again, it's not so important that you're able to derive it on the fly right now, but I want you to understand the logic right now. Okay, you can go back home and derive it yourself. That's less important. You guys can do math, I'm sure. Okay, the physics is more important right now. Okay, so now, like I said again, to summarize, we have related how many electrons are there locally in the inversion channel to the two unknowns of interest. Okay, the gate voltage and the drain voltage. We haven't really related to the drain, but we have related it to the channel voltage. Okay, so now you can see a progression from here to current voltage characteristics. Because charges we can relate to current. Okay, so let's see how that can be done. So we can make some simplifications in this particular case. In this particular case, here we can make the assumption that the electronic charge, if you ignore that small change in the depletion width, which is of course not quite correct if you assume that it's uniform, then you can make a very simple expression where QNX just becomes the oxide capacitance times the potential drop across the oxide, which is Vg minus Vt, remember the threshold to create the inversion, minus the local potential Vx. Okay. Which, by the way, if you're confused, comes from the fact that these terms right here, okay, is just Vt. The threshold voltage is nothing but the flat band voltage plus strong inversion. Okay? So that's the picture. So again, like if we just ignore the depletion charge effect, which dependence on channel, which we will put back in later, but if you ignore that, you get a very simple expression, okay? Where you can relate the total charge in the inversion layer to the oxide capacitance per unit area times the potential drop across the oxide. Okay, so it's fairly simple. So essentially, it is treating the metal oxide inversion layer as essentially a parallel plate capacitor. How much charge is stored in there? It's capacitance times the voltage drop. Okay, so it becomes a very simple model to think about. Forget the equations for the moment. Think about this from the picture of the metal oxide, and on this side you have an inversion layer. Okay, all it's saying is that you can treat that as a parallel plate capacitor. What's the charge in the parallel plate capacitor? Is the capacitance of the capacitor times the potential drop across the capacitor. Okay, so fairly simple way to think about it. That's why that approximation is kind of nice. Okay. Now, to calculate the current is relatively straightforward because we know how many charges there are. If you know how many charges there are, if you multiply by the mobility, that'll give you, the mobility times the electric field will give you the velocity. So if you know the charge, how many charges there are to calculate the current is straightforward, right? Charge times velocity gives you current density, essentially. So what do we need is the velocity. For the velocity, you need mobility times the local electric field. Okay? So all of this we know. You plug that in. So in this case, the drain current at some location x here is given by the mobility of the electrons. I'll come back to what that dash is in a second. Times the number of electrons, which is z is the depth out of the screen, times the charge density, which we just talked about right there, times the voltage divided by dx. dvx over dx is the local electric field. Yes?
And they just do absolute values so that it's non-directional?
Yes, because they're electrons, so you'll have negative charge. So, but it's not important for the current because you should know which way the current is flowing. But they will be consistent. Okay? So the current is essentially the local field, which is that, right? Times the mobility. We'll put this stuff later. Make sense of that in a minute. Times the number of charges. That's it, right? Number of charges is basically this times that. Okay? This is per unit area in this plane. That's why if you multiply it this way, you get the total charges in a small region right here. Okay? So it's pretty straightforward. Okay? Field times mobility gives you velocity times the number of charges gives you current. Okay, so now you have everything. If you plug this equation in here, you have your current voltage characteristics. Now you can relate drain current, which has, by the way, has to be the same across, right? Fermi levels is fixed. Current will be the same across the whole channel, so you can calculate anywhere, it will be the same. The drain current is now related through this equation to Vg and Vx. Now, of course, if you do the integral, you can relate Vx to Vd, because you'll integrate across the channel. So now you have all the equations that you need. Remember, we're trying to relate Id, the drain current, as a function of Vg and Vd. This is the goal. Okay, this is what we're trying to do. Right? These are the two inputs. This is typically a bias. This is typically your small signal. This is your output. Okay, that's what we're trying to do. So keep that in mind, and you plug that in. That's exactly what you get. So to get the fine, you plug this equation in here, okay, and then you do the integral. The integral goes across the channel from 0 to L, L being the length of the channel. On the other side, the integral goes from 0 at the source end. Source end, the Vx is 0, right, because the voltages are all relative to the source. So Vx is 0, and it goes all the way to Vd, which is the drain voltage. Okay. That integral is pretty easy to do because these things are all constants, right? You just have Vx, so you get a quadratic dependence of Vx, Vd actually. Okay, so pretty simple. So you get that a simple expression. So now we have this, what we are looking for. So you can quantitatively describe how the Mosfet works in this case. So you have drain current is related by some constant, which is shown in the blue circle. Forget that for the time being, and some voltage dependent term. You can see the dependence on the gate is linear. Okay, there's Vg. The dependence on the drain is quadratic. Okay, you have Vd and Vd squared. Okay. And of course, if you plot the equation, before we go through all that, if you plot the expression, we get the familiar thing we saw before. Id versus Vd is the so-called current voltage characteristics. As Vd, it's a quadratic dependence. But remember, this is all derived under the assumption that there is no saturation. Once saturates, that equation is no longer valid. Okay? So this is valid until pinch off or saturation happens. Okay. After saturation, our assumption will be that the current is essentially independent of the drain. It's just like the JFETs, exactly the same way. In fact, if you look at the curves, they look the same, right? It's basically the same thing you saw before. Okay. By the way, the reason to use Mosfets are much more popular than JFETs has to do with the fact that they're much easier to fabricate, much more economical to fabricate. That's the main reason. There are a few other things which we'll talk about also. Okay, anyway, so now let's walk through these terms here. The first term here, you can think about this as gain, right? It's the transconductance. It's how much does the current change as a function of changes in voltage, whether it's a gate or drain or whatever. In this case, it's a gate, right? Because this is directly dependent. It's a direct proportionality to the gate voltage. The drain, we have to do a differential. So that coefficient here essentially is the conductance and the transconductance of the N-channel MOSFET. How does the current change with respect to the applied gate voltage? Okay. As I said before, this equation what we have derived so far is valid for small drain voltage before saturation happens, okay, and small drain current. If we include change in depletion width with drain voltage, first of all, that was the thing that we ignored last time. That's one point I forgot. Is this part we ignored? Of course, you can put that back in. Okay, all it does is you get a square root term in the integral, which of course you can integrate. It's not impossible. You can do it yourself. It's not that hard. And you end up with an equation which looks a little more complicated. Of course, when you integrate a square root, you get a ratio 3 over 2. So it's not that hard. Okay, so you get a bit more rigorous expression. That takes into account the fact that the depletion region is changing across the channel. Okay? But that's a small effect, so don't worry too much about it, I would say, for now. But so if you look at the curves here, this is linear when the drain current and the voltage are very small. At some point, it becomes the quadratic part comes into play, and here you get a bit more of this part of it. Okay, and at some point it saturates. Okay? So just understand the physics rather than the equations so much. Okay? So the two regions where this is applicable is one is below saturation, and one, our assumption is that the inversion layer exists. That means that the gate voltage is higher than the threshold. That was an assumption. In other words, Vg minus Vt is positive. Okay, that's the assumption here. Otherwise, this is not valid. We'll talk about subthreshold later on. But, yeah.
So the small drain voltage is why we were able to get rid of the last term.
Previously, yes, that's correct. Yeah. That was the assumption of the small drain. Just means that the depletion width is relatively constant across the channel. This is okay as long as the channel is big. If your transistor is large, this is a very valid approximation. But almost all the transistors today are small, so not quite true anymore. We'll talk about that. Okay. In fact, it will become highly simplified. So a few things to consider in the linear region, where over here the transconductance is, which is essentially the slope of this curve, or in other words, the gain that you can gain by working the transistor under the linear region, is essentially the derivative of the drain with respect to Vd, and you get a simple expression like that. You can see that the transconductance is dependent on the gate. So higher the gate voltage, I can get higher gain. Okay? If my input was the drain voltage. So in principle, I can actually use this as a triode and so on. Okay, which you might have learned in your op-amp class, what a triode is, basically, amplifiers. This is the old days, the analog electronics. So it is possible to use this as in the linear region, but it's not very common to use it in the linear region. Okay? In other words, what I'm trying to say is that you can use these transistors also for analog processing, which apparently is getting, it's not my area of research, but it's getting more popular now because you can do low power processing and lots of very interesting things with that. So in other words, we are talking primarily on digital processing here, integrated circuits and so on, but you can also apply these devices over here to do analog processing, because you get this transconductance gain, which can be controlled with the gate. So you have some interesting properties there. Anyway, you should be aware of that. As the drain voltage increases, of course, as the inversion layer pinches off near the drain, right? Near the drain, like we said, it pinches it off, and you get saturation. And the drain saturation, the drain voltage where the saturation occurs, is when at the drain. So if you look at this picture, remember the voltage here is coming down. At some point, the voltage from the gate to the body here will be just at the threshold, which means that the inversion barely exists. That's the point when the pinch-off happens. Okay? Of course, it will happen first at the drain, because that's where the biggest depletion region is. Okay? The depletion eats into the inversion layer. Okay? So we can calculate very easily that the saturation happens when the drain voltage is equal to Vg minus Vt. Barely saturated. Barely inverted. Okay? Also barely saturated. That's the onset of saturation. Okay, so after saturation, we assume that the current remains constant with the drain voltage, which is, as you see here, it's flat. And we can calculate what that is by just plugging in Vd sat into the equation here or here. Okay, so you get that expression. So that's a constant current. Then we can calculate what's called the saturation transconductance. This is important because that's where the amplification happens. So remember we talked about this. The input typically is the gate. Okay, you apply a small signal to the gate, which moves these curves up and down, right? And that is what gives you the amplification to the small signal. Okay, so it's useful to understand what the saturation transconductance is, where the drain voltage, drain current, which is our output, is differentiated with respect to the gate voltage. Okay, so this is the amplification factor overall, right? So you can see it's not linear, first of all, because as you increase the gate, you get higher amplification. Which, by the way, could be a problem as well, which means you could distort your signal going in. So there are lots of things one needs to consider when you use these in devices, in circuits. But you can see, in principle, you can get very high. In order to get high transconductance, what do you need to do? Look at those terms there. Actually, it's a good question. Take 30 seconds, look at that equation. Let's say I want very high amplification. What do I need to do? Think about that. Because that's what one of the requirements, right? You want to build an amplifier, you want to design a device which gives you lots of amplification. Okay? Any thoughts? Okay. Yes, that's a good idea. Well, yes, that's true. But let's put that aside for the time. Let's ignore this part. Let's talk about the device when you make it. But smaller, that's a good point. So that's one reason to go to smaller devices, right? You can get higher amplification in principle. Yes?
Have it come out more to make the Z.
Yes, that's a good point. It has two problems. One problem is that it takes more area, which means you get to put fewer transistors in, which turns out to be a problem. Second, you increase capacitance, parasitic capacitance this way, which we will talk about later. But of course, the other things are the mobility, which we talked about. Mobility turns out to be important, right? Remember we talked about our quantum well devices with high mobility, and same principle is applied here. Also, the gate capacitance, right? So it's saying that you want high gate capacitance, which means that you want that oxide thickness to be very thin. Remember, it's inversely proportional to the gate capacitance. I told you before that all the advanced devices are very thin oxide. That's one of the reasons. Okay? So it gives you lots of, essentially what it's saying is that you can control the output current in a much more sensitive fashion to the gate. That's basically what I'm saying, by geometric control, essentially, of the device, right? I can make my channel short, I can make my gate thin. These are things we can control. Materials, less so. Okay? Okay, do you have a question? No. Okay, so let's think about the output characteristics of the Mosfet. So for the N-channel Mosfet we just saw, okay, the curves look like that. For the P-channel Mosfet, let's think about this for a second. Because they're inverted, but we need to understand why they're inverted. Okay? First of all, for the P-channel MOSFET, it's an N-type substrate, and you have to apply a negative voltage to create the channel. Right? You have to pull the holes in, you have to make it locally P-type at that interface. So you need to create a P-type channel. So obviously the gate has to be negative. That's relatively simple. The drain to source, of course, it's a P-type channel. So the holes will flow from where to where? Okay, it's a bit of a trick question because the drain and source are arbitrary, right? Remember we talked about, in fact, you mentioned this last class, they're symmetric, I can pick what I want. Okay? So, of course, the holes can flow whichever way you apply the voltage. Okay, we'll be very clear about this thing, but first of all, the source and drain are a little bit arbitrary. Because they're symmetric. These devices are completely symmetric, right? As long as they're free-floating. As long as I connect my source to my body, the substrate, I break that symmetry, then I know which one's source, which one's drain. But if I just give you, if I don't ground that, look at that picture for a second. If I don't ground that, I can't tell which one's source, which one's drain, right? Okay. The reason this is source is because this is connected to this. They're both grounded, essentially. Okay, first of all, keep that in mind. Okay, now looking here, of course it can flow both ways, but now the holes will, when I apply a drain to source voltage, where this is negative, that's positive, the polarity is flipped, the holes will flow from where to where? In this situation, look at this picture. Okay, imagine if holes, P-type channel right there exists because I've applied a negative voltage to the gate. Okay, now let's say this is the situation. I have drain voltage applied like this. Is this grounded? It's negative. Which way will the holes flow? Yes, source to drain, right? Because that's a negative voltage. It will attract the holes. Which way is the current? Same direction, yeah. Okay, so now you can see the VD is negative, right? And the current is, by convention, is always referred from drain to source. And the reason for this is actually a little bit historical. The fact is that most silicon wafers used for devices are N-type, which means that P-type. So the N-channel MOSFET is the conventional MOSFET. When you need to make a P-type MOSFET, you have to make an N-type well. We'll talk about that in chapter 9. Okay? That's why the drain to source current is always considered positive. That's just a convention. Okay? With that convention, you can see, when the drain voltage is negative, the drain to source current is negative. Okay? Because the current is really flowing from source to drain. Okay? And then the IV curves make sense. So make sure you're fairly clear on what those mean. And of course, for the P channel, where will saturation happen? So I want you to think. Actually, this is a good exercise. Why don't you take out a piece of paper and draw what. Actually, I'm going to go back. Draw this picture for the P-type channel. Yeah. This picture. Take out a piece of paper and draw this picture for the P-type channel. Okay, let's start, and I'll get you started. Let's imagine that's just a metal gate. Okay, it's an oxide insulator. Then it's a P-type channel, so it's an N-type substrate. Okay, this is the N substrate. So we have a source, which is P plus. Okay. Then we have a drain, which is also P plus. Okay. That's my oxide. I want to know, how does the depletion layer look like here? It doesn't matter. Yes, because inversion exists. Yeah, assume it's about threshold. Yeah.
Is it below the pitch off for saturation?
Let's say it's close to saturation. I want you to show me where the saturation occurs. So I assume that it is saturated. Yes. Yeah. More good question. I didn't think about that. Give it a shot yourself first. Okay. So, okay, let's see how would we address this. Have any thoughts?
I think would it just be opposite of this one, where it's just...
Let's not go jump to the answer. Let's see how we get there. how we get started? What do we need to know to understand this? You have some thoughts?
Well, we know it's in saturation, so there should be some kind of depletion region, because it's pinching off, so it has to be cutting.
Well, yeah, the depletion region exists most of the time, but okay, let's start here. Okay. some junction, right? You have a junction, you apply voltage. Okay, so there is no voltage difference between here. Okay, so that's just the regular depletion. You have a PN junction which is basically shorted, right? You have depletion region. No? Okay, no current flows, but there's still a depletion region. Okay, so there's some depletion region there. Whatever. Okay, don't know what that is, but let's say. Did you have something to say?
I was just saying, I would assume that we have a very high negative charge on D, correct?
Yes. So what does that mean?
So it means that we're going to make hopefully repelling the negative and making it area of holes.
Correct. So this will become more depleted, right? So okay, this is easy because it's just shorter. But here it's even easier because you just reverse biasing it even more, right? So PN junction here, you're reverse biasing it essentially. This is 0, remember? Okay. You reverse bias the PN junction, what happens? Depletion region becomes bigger. Okay? The depletion region, we are ignoring any depletion in here because it's so highly doped. So the depletion region here will essentially extend all the way to the end. Okay, so we look like that, where this is depletion, this is inversion. Without doing any calculation, right? Does that make sense? Now, I want everyone to kind of think about this. I mean, this is without understanding anything to do with Mosfets at all, right? We're just talking about 2 PN junctions. 1 PN junction here, 1 PN junction here. Okay? Yes?
I thought that the negative charge would attract the holes and essentially have it tilting the other way.
Let's see. This?
Yeah. So the negative on that side would attract more holes. So I would expect the inversion to be thicker on that side.
No, the inversion is primarily controlled by the gate. Okay, imagine that's
well,
some
the
fixed
width
voltage.
is.
Yes.
But the tilt of it, doesn't that depend on which?
It depends on the local potential, right? It depends on the difference between the gate and the local channel potential. Remember, that's this Vx right here. Okay? And the Vx here will be pretty negative as well, which means that Vg minus Vx will be basically 0, which means that I don't have much of a potential difference to attract my holes. That's another way to think about it. Okay? So depletion is one way to think about it because I think it's easier to think that way. But the inversion, you can also think about inversion, right? Inversion happens because, okay, let's look at any random point in the channel. The reason inversion happens is that the point here and there is a potential here. So the reason holes will come to say this point is because the potential here is more negative than the bulk, so the holes will come close. Okay, and the reason it's more negative is because you're applying a negative voltage here, right? Because there's a drop and so on. But it is the local potential compared to that gives you that hole of the holes. Yes?
But those holes are going to be up against the oxide there, correct?
Yes, yes.
Okay. So I saw that space there. I thought you were saying that was...
Oh, this is oxide. Nothing happens here. Okay. Okay? Nothing happens here for now. Okay? That's a bit more complicated, but think about it from the depletion region. That's probably the easier way to think about it. Okay? Okay, go back and redraw that again, okay, because that's important to understand the difference between the N channel and the P channel, because we should get going. Okay, the input-output characteristics is what we talked about just now, which is current, drain current as a function of drain voltage. You can also define what are called transfer characteristics, which is drain current as a function of gate voltage. Like I said before, when you do signal amplification, the signal goes into the gate, okay, and the output comes in the drain current. So the transconductance is essentially that gain. So you can plot directly the drain as a function of gate voltage, okay, And we know that when the gate voltage is below threshold, there's no current because there's no channel. At some point, it will start going up a little bit, and that's so-called sub-threshold region, which we'll talk about later. And then after threshold, it forms a linear region. This is where strong inversion happens, and pinch-off has not happened. So you have a channel, and saturation has not happened. Okay? So this is the linear region. Then after a while, some kind of saturation happens. Okay? Saturation, of course, happens with respect to the drain, but with respect to the gate, you get some additional nonlinearity, which is shown here. Okay? So this equation is exactly the same as what we had before. This should be a straight line, but at very high gate voltages, you get a deviation from linearity because you get very high electric fields in the transverse direction, perpendicular to the flow of electrons. Okay? Okay, so let's think about that also for a second before I keep going. Let's look at the picture. Okay. Let's look at this picture for a second. Okay. If I apply higher and higher gate voltages, what is happening to the electric field? It's increasing, right? So what happens to the electrons here? These are electrons. N-channel. P substrate, N-channel. As I increase my gate voltage, what happens to these electrons?
It's stronger attracted to the gate.
Yes, they move closer to the gate. Okay? They move closer to this interface. Right? They like to get attracted. What is at the interface? There's a difference. So that's oxide. What is this material? It's silicon. Right? At the interface, what do you have? You have imperfections between oxide and silicon. You have a crystal lattice difference. Okay? Which means, of course, what does imperfections mean? That the carriers will scatter off it. Right? Remember we talked about mobility, and when you increase doping, you get lower mobility and things like that. Exact same thing happens here. As the electrons get closer to their interface, they scatter more because they see more of those dangling bonds and whatever, charges that are trapped there and so on and so forth. They scatter off, which means that their mobility starts going down, which means that I would expect the current to go down as well. Okay? Instead of going straight up, I would expect the current to curve a little bit, which is exactly what you see. Okay? That's what's going on here. Okay? You also get other things like charges which are trapped in the oxide can also cause scattering and so on. But the picture is very straightforward. Okay? In other words, if you look at the amplifier gain, which is how much current amplification I can get with respect to the gate, I see a peak. Okay? Above that peak, I essentially lose because I'm scattering more. Yes? You got a question? Okay? So if you look at the character, so this was before saturation happens. Okay? If you look at the situation after saturation happens, it's fairly similar. The only difference now is that you get the ID set is now related to this square. Okay, so if you plot the square root, you get a straight line, and slope gives you the saturation transconductance. Not terribly important, but just keep that in mind. It's exactly the same equation as before, except that you have the square term. Okay, this is the same expression as we had here, except that VD is now VG minus VT. So you have two terms there. That becomes a square, right? It's fixed with respect to drain. It only depends on gate. Anyway, don't worry too much about it. Okay? Okay, so let's look at the particular example problem from the text very quickly. Let's see what's the time. Okay, good. So it's a very typical problem, so let's walk through it fairly quickly. So you have an N-channel Mosfet with a gate oxide thickness of 10 nanometers. So it's pretty big for a gate. Typically, remember earlier we talked about 1 nanometer and so on, so it's pretty big. The threshold voltage is 0.6 volts, so that's very typical. Okay, it's typically between 0.5 and 1 volt. Okay, and we will talk more about this later on. It's a very important. It's the most important parameter that you get to play with in your transistor design. The width of the channel is 25 microns. The length of the channel is 1 micron, so it's fairly big. For the sake of argument, remember I showed you some pictures where the length of the channel was like 10 nanometers. This is 1,000 nanometers. Okay. Calculate the drain current at VG equals 5 volts and VD equals 0.1 volt. Okay. So to solve this, it's pretty straightforward. Plug it in, right? So what do you need? You need to go back to this equation. So first of all, we need to find out if it's within threshold or not. Okay, so the condition, what's the gate voltage? It's 5 volts. What is the threshold voltage? It's 0.6 volts. So of course, it's above threshold. That's the first question to answer. The second question to answer is, what regime is it? Is it linear? Is it saturated? Okay. The condition for saturation is that the drain, remember, saturation is related to the drain voltage. The condition for saturation is that the drain voltage is greater than or equal to Vg minus Vt. Remember, that's the situation where right at the drain, you get pinch off. So the depletion eats into the inversion. Vg minus Vt. So what's Vg minus Vt? It's 5 volts minus 0.6, so it's about 4.4. And Vd is 0.1. So it is not saturated. It's pretty straightforward. So it's a linear regime. The rest of the is pretty straightforward. But that's the logic. The rest of the thing, you just plug in the numbers. Not so important. Okay? Now what happens when Vg is 3 volts? You're still above threshold. Okay? 3 minus 0.6 is 2.4. It's still in the linear region, and so on and so forth. Okay? And you can do that. Now these two are straightforward. Actually, this part, let's think about that a second. When Vg is 3 volts, it's above threshold, so the channel exists. But think about whether it's under saturation or linear regime. Okay, why? Yeah, okay. Okay, so it's pretty straightforward as long as you follow the logic. And applying the equations is simple. You don't need to worry about that. What happens for Vd equals 7? Of course, it's probably under saturation. The current remains the same, and then you can calculate the issues. Okay. Okay. So let's see how did they do it? Okay. So you have to find the transconductance, which means you need to know the capacitance, all this stuff, and you can walk through it. I won't go through it in much detail. Okay. So the first part is linear region. Second part is saturation, as you can see. And 7 volts is still saturated, so ID will not increase. No. That's it. Okay? So you should be comfortable being able to analyze problems like that. Okay. Okay, now we will start in looking at some non-idealities into the model. So far we assumed that the Mosfet is essentially ideal. Okay, you apply voltage, you have current flow, and we ignored quite a bit of realistic things that happens, which some of them are important, especially for the most advanced transistors. So we need to take these into account. The first one is the mobility. Okay, this is what we just discussed. As the gate voltage is increased in the case of an N-channel device, okay, made more positive, the gate field across the oxide increases. Okay, because it's just the voltage divided by the thickness of the capacitor, thickness of the oxide. Okay, so the question for how does mobility of electrons change in the channel relative to the bulk? This was a question we just discussed. Of course, the electric field is orthogonal to the flow of the electrons. So this is not the typical saturation we talk about when we talk. Earlier we had a plot where we plotted electric field as a function of mobility. Velocity is a function of electric field, and it was a straight line, and at some point it's saturated, right? And the slope of this line was mu, mobility. Okay? This is a different issue because in this case, the electric field was in the same direction as the flow of the bulb, in collinear, the opposite direction. Okay? In this situation, the electric field is, that's V, that's E. Okay? It's a different situation. But the same kind of effect happens. Why? Because we talked before, the electrons are pulled up towards the interface. So more electrons see the interface, more electrons scatter, you expect the mobility to decrease. So it's a very different effect. But the implications are very similar. Okay? So, oops, that's small. So essentially it says at the interface, the carriers, the electrons, the holes, they scatter off the impurities and trap charges. So you also have, and we'll introduce this before, in a little bit, is that although we assume that the oxide is essentially a pure insulator, in a real oxide you always have some trapped charges. Okay, there are impurities, which means they're sodium ions or whatever, which can also scatter electrons. They can have Coulombic scattering. So if you have a charged particle and another charged particle is moving next to each other, you can have some scattering. Okay, so-called Coulombic scattering, and that would also force the mobility to drop. Okay. So then so the next question was, how does the mobility change with gate voltage? I kind of answered that. If you plot mobility as a function of gate voltage, you would expect it to drop, right? Because of the extra scattering. So the higher gate voltage pulls the electrons closer to the interface and induces more scattering and essentially decreases the mobility. So you would expect at some point that the current should come down, which is what we saw in the transconductance plot before. Okay. What does it mean for the drain source current? It's basically what I said. I guess I should have you guys answer these questions. Okay. Next one. How will the mobility change with drain voltage? That I want you to answer. In fact, I kind of answered it already, but I want you to spend a minute thinking about it. So, I want you to picture the channel, okay, and see you have a fixed gate voltage, okay, and I'm increasing the drain to source voltage. Think about the mobility of the electron. Okay? And this effect is very important for short channel devices, the most common transistors today. So spend a minute, think about what will happen. How will the mobility change with the drain voltage? And you can discuss with the neighbor. You can discuss with me. What do you think? Good. Okay. That's good. So at least someone knows. Okay. So any thoughts? Not you guys. Unless you have any thoughts. I don't pick on you. Sorry. It's more useful if you think yourself and you will remember these things yourself. I don't want to say. What do you think? Yes, exactly. Yes, exactly. Yeah. So what does that mean? It's apply the drain voltage. Okay. So everyone. So increase the drain voltage. Yes. What happens? The field increases.
Is that where the electrons get more attracted to the gate?
No. Remember, the gate is fixed. The gate is fixed. So imagine a fixed gate voltage. It doesn't matter what's going on at the gate. You're increasing the drain to source voltage. Okay. So the electric field from the drain to the source, which is in the direction of the propagation of the electrons, will increase. Okay? It will increase, which means that we have a situation which looks like that. Like this, right? The same direction and so on. So increase this field, this will saturate. The mobility will, at some point, will saturate, and this is called so-called ballistic transport. In fact, most of the transistors today actually operate like that, in this kind of a regime. What does that mean to the current?
If the electrons are moving more quickly, the current should increase. You have more electrons going by.
Yeah, so of course, if I plot current as a function of the field, current is increasing, but at some point,
It should saturate.
yes, it will saturate. But, so the current saturates with respect to the drain. Think about that for a second. What is the other situation when that happens, which we just talked about? Just now, in the Mosfet. It is, let's see. Oops, it's right here. Right? It is pinch off. Right? That's when the depletion eats into the inversion layer. Inversion layer disappears at some point near the drain. So think about what you just said for a second. Now I have current saturation without pinch off. Right? Which means that almost all of today's transistors almost always operate under saturation. You don't need to have pinch off. So again, let me repeat this a second. Okay? In the situation we talked about, when the electric field is very high in the direction of propagation of the carriers. Okay, let's go back to the picture. Okay? At some point, the mobility saturates. Okay? I'm increasing the drain voltage here. Okay? At some point, the drain voltage is so high, the mobility essentially doesn't increase anymore, which means that if I increase the drain voltage, the current doesn't increase anymore. Current is saturated, but I don't have pinch off. Channel exists everywhere. Okay? And this is what's called a ballistic transport in a transistor. And if you look at most of the advanced transistors, this is basically how they work. The equations are a little bit different, clearly. Okay? That's a very important distinction from a modeling perspective. Okay? Okay, so that's one distinction. We won't go into what of course, to model this is not that hard, right? Because you know what the mu saturation is, and mu sat times the electric field, which approximately is the Vd divided by the length of the channel, will give me the velocity of the electron, right? Times the number of electrons, times the charge, times the Z will approximately give me the current. So it's not hard to model, so we'll go through it. Okay. It becomes a much simpler model. In fact, I think that's what's coming up next, if I remember right. Okay, so of course, like I said, most of the transistors today are very short channel. So the question is, how does that impact it? Of course, the field is one, but there are a few other things. Okay, so let's see. There's probably a question. Yes. Okay. What happens to the longitudinal electric field drain to source when the channel length is small? You guys just thought about this. So what happens? Yes. So even at the same drain voltage, if I just decrease the channel length, the field can increase. The same situation, right? So what happens? Mobility saturates, current saturates without pinch off. Same kind of thing. Okay, so what? Okay, I answered my own question. What happens to the carrier mobility from drain to source? At some point, it will saturate, even at a very low drain voltage. That's a key. Okay, even at very low drain voltage, if the channel length is so small, tiny drain voltage can give you a huge electric field that the mobility saturates, current saturates. Which is fine, as long as the device is used for amplification, that's fine, right? Because you want it to be under saturation in any case. And it's kind of good that you can have it at a very low voltage, because you don't want to have huge voltages in your integrated circuits. Okay? That's a good question. Write down an equation for the current. Actually, I kind of wrote it down, but I want you guys to think about it yourself. Okay? Do it yourself. Take 30 seconds. Okay, what is the current? Under saturation. I don't think it's in the text. Just think about it. Okay, current is just flow of electrons, okay? So your number of electrons, how fast they are moving, velocity, that's it, right? Speed of electrons multiplied by number of electrons, that's the current. Nothing to it. Number of electrons, you know. How many carriers are there in the inversion channel? Qn, right? We just looked at. So you just leave it at Qn. You don't need to actually write anything down more complicated than that. How fast are they moving? Yeah, mobility times the field. What's the field? Yes, the drain voltage divided by the length of the channel. Okay, so now we have a very simple expression which relates current to the drain voltage, right? You don't even need to think, it's in your head. You don't need to do any math. It's linearly proportional, more or less. Of course, the charge Qn, the first term there, depends on the gate voltage, clearly, which is more complicated, but it's the same as what we did before. So you've already seen that before. Okay, so approximately, more or less, that's it. Oh, this is an even simpler way to think about it. You can think about it from a capacitance perspective. So the Qn, so this part here, let me just rewrite that. Okay. So I is, what did we say? We had a charge, Qn, times mobility times the field, Vd over L, more or less. Right? The Qn can be written as the capacitance of the oxide multiplied by the gate voltage, okay, minus whatever is required to create the channel, okay, which is basically threshold minus Vt. Vt is what's required to create the inversion layer. So you have to subtract that, and this is the voltage that comes across the oxide times its capacitance gives you the charge. Right? Treating the oxide inversion layer as a parallel plate capacitor. Basically, that's it. Right? So you have a channel here, positive charges here. What is the charge here? This is what that was the question. Right? Pretty simple. Okay? So the ID under saturation, when you have a short channel Mosfet, is essentially Z. Of course, you have to have the Z here because what's that? That's the channel distance coming out, because C is all with respect to unit area. So CCI, the voltage times Vs, which is the saturation velocity. Okay? Channel width, that's the total charge, that's the saturation velocity. Okay? And you can compare this to our previous equation we had for saturation. Okay? This is what we just derived a couple of slides ago. Okay? The difference clearly is that the saturation current here is proportional to square of Vg minus Vt, whereas saturation current here is proportional to Vg minus Vt. So if the key difference is if I plot my VD ID curves if I increase this, these become equidistant as opposed to being nonlinear. So it's a very similar situation we had in the JPEG. Okay? In other words, the transconductance is independent of the gate voltage. Okay? It's a linear dependence as opposed to a square dependence. Okay? So when you model a short channel Mosfet, it looks very different than a long channel Mosfet. And we have to be careful about this situation. Of course, if you go back and use the full equation, you can still, well, actually you can't, sorry, my mistake, because you have assumed here that the mu is a constant, essentially. Okay? It's not a constant because it saturates. Okay. Okay, so let's cover this also. This is kind of interesting, actually. So the next part for a real device, especially if you're a device designer, so if you're working at Intel or IBM and you want to design a device, one of the first things that you will worry about is what is the threshold voltage. Now, threshold voltage is very important because this is what you need to barely turn on the device. Okay? You don't want that to be too high. If you make that too high, that means in your integrated circuit, you need to provide a power supply that can go to a high voltage that you don't really want to do. Okay? Because it's expensive, it's hard to do, all that stuff. So you want to keep it relatively low. But you don't want to make it too low. If your threshold voltage is too low, then any little noise in the circuit can turn on the transistor, and that's very bad. Right? You will get anomalies, all that kind of stuff. Also, you don't want the transistor just be on and you'll have leakage current and you'll have power loss and your battery will die off. You'll get heating and all that kind of stuff. So the choice of the threshold voltage is very critical in an actual working, practical application. And there are a few things that a device designer can do during the fabrication of the device to design for the threshold voltage. Okay, this is very important. If we look at the expression for the threshold voltage, okay, we saw this before. We have 4 terms here. Okay? The first term is essentially the difference between the work functions of the metal and the semiconductor, phi ms. Work function of the metal minus work function of the semiconductor. Okay? That causes some bending of the bands, okay? To match the Fermi levels, if you remember. Then you have a few terms here. This term is the charges inside the insulator, Qi. So that's the impurities within the, or interface charges, okay? It's actually, sorry, that's the inversion charges, my mistake. I haven't included the interface charges, the oxide charges yet. So ignore what I just said. Qi is the inversion charges, okay, just the inversion layer. Okay, pretty straightforward. Qi over Ci is the voltage required to create the inversion layer. Okay. The Qd is the depletion charges. Okay, you have to have a depletion region, so you have to have some voltage drop there. And 2 phi f is the band bending for strong inversion. Okay, so those are the terms you can control. Now, if you think about it, you can control that. We already saw that by the doping of the substrate, right? That's basically the IF is essentially the distance between the intrinsic level and the valence band for the p-type substrate, or the conduction band for the n-type substrate. Okay, but it turns out you can control these other things as well. Of course, the phi ms is straightforward because you can pick what metal you want to use. Silicon is typically semiconductors, you don't have much choice there. But the metal you can pick. So you have some tunability there. So let's talk briefly about that and we'll start. Okay, first of all, phi ms is basically this, right? Typically, in a typical situation, you have a metal oxide semiconductor. This is something you've seen before. When the metal work function is smaller than the semiconductor work function, the bands have to bend because the Fermi level, there's no current flowing, so the Fermi level here has to match. Okay? Nothing special here. The problem, of course, here is that if you look at the situation right at the interface, what type is this material at the interface? Yes, it's an N-type because the intrinsic level has gone below the Fermi level. Its Fermi level is closer to the conduction band. It's a little bit N-type. You have electrons trapped there, essentially. So it's inverted naturally. This is the so-called device which is always on. And it's also called a depletion mode device because there's a depletion region which naturally exists because of the work function differences. This is a problem, like I said, and we'll discuss this later on. Okay? Now, of course, we can avoid this problem by simply choosing a metal whose work function is larger and closer to the work function of the semiconductor. Okay? Now, the choice of metal, although there are several metals to work with, it's not infinite in the sense that there are some metals which are easier to process, and we'll talk about processing in Chapter 9. But there's some metals which work well at low temperatures. You don't need high temperature processing, all that kind of stuff. So that kind of restricts what you can use for the gate material. Okay? So for most modern transistors, what people do is they use very heavily doped silicon instead of an actual metal. And the advantage of that is you can control that work function by changing the doping level, almost arbitrarily. Of course, you want it to be pretty highly doped, okay, because you want it to be almost metallic. But this is usually what happens. Okay, this is an actual transistor, typical transistor. You have a silicon substrate, like I said. This is an N-type substrate. Okay, typically. Okay. Now you create a well here, which is an N-type well. So a small local region which is N-type, that is your N-type body or substrate for the Mosfet. Then you create the P plus source or P source and P drain. Okay. Then you have a gate electrode, and you have a channel and all that, and you have metal contacts which come to the source, which come to the drain, which come to the gate. And the gate electrode is what we are talking about. The gate electrode should be heavily doped. But I guess we'll save this for next class, but I want you to think about what type should the polysilicon actually be. We have 2 minutes, so I want you to think for the next minute. Okay, if you have a polysilicon gate, as I said, and it's heavily doped, what type should it be? Should it be N-type, P-type? Think for a minute. And the hint is to think about the band diagram. It's not in the text either, so I want you to draw it yourself. Okay, I guess I'll stop here and ask and have you sleep on this over the weekend. Do this exercise before next class, okay? Look, you have the slides online. Just look at it. Okay, what type should the polysilicon gate be doped? Draw the band diagram. Okay, depending on what you pick. What if it's an N channel? It's an NMOS device. What should that be? And draw the band diagram. Okay, that's your homework for today and tomorrow, until I post the other problem set. Okay? Oh, the homework is due today, so don't forget.
So that's N-type silicon, P-type, DNS.
Yes.
Okay, just want to make sure.
N-type what? Sorry, I didn't hear you.
I just want to make sure.
It's a PMOS transistor. This is opposite to what you saw before. So look at the body is N-type, as opposed to body
that
goes
answers my
P-type.
question.
Yes.
I know what it is. All right.
Yes. It's the opposite of what we saw. Yes.
Can I ask you a question about the homework again?
Yes.
I'm sorry, I always talk
That's
about
all right. Yeah.
So one of the questions asks to decide if something's ohmic barrier or Schottky. And I know for ohmic, it's like the work function of the silicon is greater than